Hello friends and students. I would like to continue the haloalkanes and haloarenes. In the part 2, I am going to discuss you about the physical and chemical properties of haloalkanes and haloarenes. In part 1, you studied about the definition, classification and preparation of haloalkanes and haloarenes. Let us see the physical and chemical properties of the haloalkanes, particularly alkyl halides. Okay, so I am Dr. K.S. Kumar, and of course I am using the slides prepared by Venugupta sir. Okay, we shall move. Regarding the properties, I would like to discuss about the physical properties first. See, in this slide itself, you can understand many things regarding the physical properties of these haloalkanes. The first point is the boiling point. How the boiling point varies. To remember it, you should remember that the order of the boiling point decreases in this order. So that is shown in this slide. That is, so the alkyl iodides possess the highest boiling point, then the alkyl bromide, then the alkyl chloride, then the alkyl fluorides. So in this you can observe one thing. As the size of the halogen atom decreases, the boiling point decreases. Remember this point. So size of the iodine is more than the bromine, size of the bromine is more than the Cl, and Cl size is more than the fluorine. Therefore, the boiling point decreases from iodide to fluoride. Okay. So the next thing we have to consider this one. Here you can see. So the second line. So first one is the primary alkyl halides. Second one is also a primary alkyl halide. Third one is also a primary alkyl halide. Okay. So in this case, you can observe the first one is a linear chain. Carbon chain is linear. There are 4 carbon atoms and 4 carbon atoms are in a chain. Whereas in this case, there are 4 carbon atoms, but 1 carbon atom is branched. And in this case, it is more branched. So from this you can understand it. You can compare any such alkyl halides. So if the branching is more, boiling point is less. If the unbranched carbon chain is there, the boiling point is more. Okay. So you have to consider this point. Carbon chain is linear here. It is less branched, it is more branched. More the branching, less is the boiling point. That's the thing you have to remember. In the third example, you can see the first one is a propyl group. Second one is a ethyl group. Third one is the methyl group. So carbon length decreases here. As the length of the carbon decreases, the boiling point also decreases. See, just by 3 lines you can understand many things. In the first line you can understand as the size of the halogen atom decreases, the boiling point decreases. In the second line you can understand as the branching increases, the boiling point decreases. So in the third line you can understand as the length of the carbon chain decreases, the boiling point decreases. So ಈ ಪಾಯಿಂಟನ್ನು ನೀವು ಚೆನ್ನಾಗಿ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. ಸೊ ಹ್ಯಾಲೋಜನ್ ಸೈಜ್ ಜಾಸ್ತಿ ಇದ್ದರೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಇಲ್ಲಿ ಕಾರ್ಬನ್ ಚೈನ್ ಲೀನಿಯರ್ ಇದ್ದರೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಆ್ಯಂಡ್ ಕಾರ್ಬನ್ ಚೈನ್ನ ಲೆಂತ್ ಜಾಸ್ತಿ ಇದ್ದರೆ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟು ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಇನ್ ದಟ್ ವೇ ಆಲ್ಸೋ ಯು ಕ್ಯಾನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್. ನೆಕ್ಸ್ಟ್ ಪಾಯಿಂಟ್ ನೋಡೋಣ ಇಲ್ಲಿ ರಿಗಾರ್ಡಿಂಗ್ ದಿ ಬಾಂಡ್ ಸ್ಟ್ರೆಂತ್ ಆಫ್ ಹ್ಯಾಲೋಆಲ್ಕೀನ್ಸ್. ಸೊ ಯಾವ ಥರ ಹ್ಯಾಲೋಆಲ್ಕೀನ್ಸ್ ಬಾಂಡ್ ಸ್ಟ್ರೆಂತು ಇಲ್ಲಿ ವೇರಿ ಆಗುತ್ತೆ ಅಂತ ಇಲ್ಲಿ ನೀವು ಗಮನಿಸ್ಬೋದು. ಇಲ್ಲಿ ಬಾಂಡ್ ಸ್ಟ್ರೆಂತ್ ಇನ್ ಕೇಸ್ ಆಫ್ ದಿ ಫ್ಲೋರೈಡ್ ಈಸ್ ಮೋರ್ ಆ್ಯಂಡ್ ದ್ಯಾನ್ ದಿ ಕ್ಲೋರೈಡ್ ದೆನ್ ದಿ ಬ್ರೋಮೈಡ್. ಇದಕ್ಕೆ ಸಿಂಪಲ್ ಅನಾಲಿಸಿ ನೀವು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಾಗಿರೋದು. ಸೊ ಆ್ಯಸ್ ದ ಸೈಜ್ ಆಫ್ ದಿ ಹ್ಯಾಲೋಜನ್ ಆಟಮ್ increases, the bond strength decreases. As the size increases, the bond between the carbon and halogen becomes weak and it can be separated very easily. Therefore, the bond strength decreases. So remember, size of the halogen kadme idre bond strength ಜಾಸ್ತಿ ಇರುತ್ತೆ. Fluoride is more, carbon fluoride bond, fluorine bond is more stronger than the carbon iodine bond. Okay, ಈ ಆರ್ಡರ್ನಲ್ಲಿ ಇರುತ್ತೆ. Next physical property regarding the dipole moment. So dipole moment decreases as the electronegativity of the halogen atom decreases. So for that you need the knowledge of the electronegativity. Electronegativity is the ability of an atom to attract the bonded electrons towards itself. So as you know, the electronegativity of the fluorine is highest among all the elements, of course. So among the halogens, so fluorine is having more electronegativity and the iodine is having the less electronegativity. Dipole moment decreases as the halogen electronegativity decreases. So from fluorine to iodine, the dipole moment decreases. This is a common property we studied in the other case also. Okay. So next one is regarding the this one, haloalkanes, though polar but are insoluble in water. This is one of the question. Why haloalkanes, since even though they are polar in nature, the bond between the carbon and halogen is polar. But in general, polar compounds should be soluble in polar solvents like water. But these haloalkanes are insoluble in water because even though they are polar, they are not able to form the hydrogen bond with water. Therefore, they remain insoluble in water. The next point is regarding the density. So density order also you can see. So as the halogen size decreases, the density also decreases. So alkyl iodides have the more density than the alkyl bromide, than the alkyl chloride, and least density is the alkyl fluoride. So density depends upon the size of the halogen atom. So as the size of the halogen atom decreases, the density also decreases. Okay. There is an example here. So you can see the length of the carbon chain. So if the carbon chain is less for a given halogen atom, ಪರ್ಟಿಕ್ಯುಲರ್ ಆಗಿ ಯಾವ್ದಾದ್ರು ಒಂದು ಅಯೋಡೈಡ್ಗೆ, ಕ್ಲೋರೈಡ್ಗೆ, ಬ್ರೋಮೈಡ್ಗೆ ಕಾರ್ಬನ್ ಚೈನ್ ಕಡಿಮೆ ಇದ್ದರೆ ಡೆನ್ಸಿಟಿ ಜಾಸ್ತಿ ಇರುತ್ತೆ. ಡೆನ್ಸಿಟಿ is more if the carbon chain is less. So number of carbons are less. So in this case you can see methyl iodide is having the greater density than the ethyl iodide than the propyl iodide. So ಅಂದರೆ density of the lesser carbon is having the highest value. So idondu slides alli, in this one particular slides you can understand many things, you can tackle many of the neat questions or this one CET questions. Okay, so you have to understand it very clearly. So how the trend varies regarding the physical properties of the haloalkanes. Then we shall move towards the chemical properties. To understand the chemical properties, so as you know, the chemical reactions are nothing but the bond breaking and bond making processes. So in chemical reaction, some of the bonds are going to be ruptured and some of the bonds are going to be formed. So which bond is going to be cleaved easily, you have to understand. So in alkyl halides, you can see, so that is in haloalkanes, you can see, so there is a bond between the carbon and halogen. As you know, the halogen atom is more electronegative than carbon atom. So as it is more electronegative, it attracts the shared electron slightly towards itself and acquires a slight negative charge. As a result, the carbon acquires the slight positive charge. So in general, I can say, totally my intention is to say that the carbon-halogen bond is polar in nature. So the polar bond is very easily ruptured. It is going to be cleaved easily. The reactions of the haloalkanes depends upon are due to the breaking of this bond, carbon-halogen bond, since it is polar in nature. Most of the chemical reactions of the haloalkanes are nucleophilic substitution reaction. So we generally call them as nucleophilic SN reactions. So nucleophile, you know the definition of the nucleophile. Nucleophile is one which is electron rich in nature. It replaces the halogen atom by pushing the electron, okay, towards the halogen atom. So halogen becomes an allied ion and the nucleophile is going to join here. So this nucleophile may be OH group, it may be a CN, it may be NO2, or it may be any other nucleophile. Okay, so the reaction are due to the bond breaking of this carbon halogen bond, and that breaking is actually results due to the attack of the nucleophile. So most of the reactions, I am telling it repeatedly, most of the reactions are nucleophilic substitution reactions in haloalkanes. Let us see some of the reactions which are nucleophilic substitution reactions. Okay. Yes. In this slide it is given. So all the chemical reactions of the haloalkanes or SN reactions are given in one slide. So taking this ethyl bromide as an example. If you take the aqueous potassium hydroxide. So aqueous potassium hydroxide is going to give you OH minus as a nucleophile. That OH minus replaces this Br and results in the formation of C2H5OH, ethyl alcohol. And this potassium take up this Br and becomes potassium bromide. So nucleophile here is OH minus. So it generates in the presence of the aqueous medium. So aqueous potassium hydroxide. So changes replaces this Br by the OH group and it results in the formation of the ethyl alcohol. Similarly, the other nucleophiles you can suggest is ammonia. So you can see ammonia also generates the NH2 as the nucleophile. So that Br will be replaced by the NH2 and results in the formation of the ethylamine. Okay, ethylamine. But this reaction doesn't stop in this stage. The hydrogen atoms of the ammonia are continuously gets replaced. If you continue to the reaction, so another hydrogen atom will be replaced by the C2H5 and another hydrogen atom also replaced by the C2H5. So successively all the hydrogen atoms of the ammonia will be replaced by the ethyl group in this nucleophilic substitution reaction. First product is the ethylamine, second product is diethylamine, third product is the triethylamine. Interestingly, this reaction doesn't stop even in this stage. It reacts with one more mole of the ammonia and results in the formation of the salt, and that reaction is called ammonolysis. It is called tetraethyl ammonium bromide. So this salt also formed and that particular reaction is called ammonolysis. Generally these reactions are called ammonolysis. Suppose if it is stopped here in the first step, it gives you ethylamine. If it stops in this stage, it will give you diethylamine, similarly triethylamine, etc. Okay, the next reaction with the potassium cyanide. So potassium cyanide property, it's a very, very powerful nucleophile generating agent. It deionizes very quickly and results in the formation of the K plus and Cn minus ion, and the Cn minus ion replaces this Br and pushes this Br to be as Br minus, and that Br minus combines with this potassium and becomes potassium bromide, and interestingly you will get a product called ethyl cyanide. Ethyl cyanide is going to be formed. Okay. Similarly, you can go to another nucleophile like silver cyanide. In the silver cyanide, so you won't get the ethyl cyanide as in the previous case, but you will get the ethyl isocyanide. For that, the nature is different. So the nature of the potassium cyanide is different from the nature of the silver cyanide. So potassium cyanide is ionic in nature. It produces Cn minus ion more and less number of this. The dissociation is maximum, ionic nature. Whereas this AgCN is not much ionic. It is covalent in nature. Therefore, so the resulting product is the isocyanide. Ethyl isocyanide is going to be formed. So ionic nature, covalent nature is very simple. It ionizes completely and produces Cn minus ion. Whereas this one doesn't ionize since it is ambidentate in nature. So that Cn possesses the unshared pair of electron. So that those electrons will be used to form the bond between the carbon and nitrogen, and therefore you will get the isocyanide. And the next reagent is potassium nitrite. So KNO2. So it produces the NO2 nucleophile, and that Br will be replaced by the NO2. So you will get the ethyl nitrite. Okay. Okay, so O is the bonding, that is a bridging agent. So ethyl nitrite will be formed. So there again, it is ionic in nature. That's the explanation we give. So here, in the next reagent, AgNO2, same type of reagent. This is silver nitrate, whereas there is a potassium nitrate. It is again the covalent nature, so that produces the nitroethane. Here, the ambidentate nature of this NO2 group was also responsible for the formation of the ethyl nitrate and the nitroethane. Here, the nitrogen involves the formation of the bond between the carbon with the carbon, and whereas here oxygen participates to form the bond with the carbon atom. Okay, so here this reaction is called Williamson's synthesis. This reaction is also called as the Williamson synthesis. Next thing is the that is sodium alkoxide. So here you can see that one sodium alkoxide is going to be formed. So that sodium alkoxide NaO results in the formation. Sodium combines with this Br and forms a sodium bromide. So you will get this ether. Generally, you will get the ether. So, for example, if you react with sodium ethoxide, you will get the diethyl ether. So, you will get, if you react with sodium methoxide, you will get the ethyl methyl ether. Ethyl methyl ether, mixed ether will be formed. So, that is the ether formation, and this reaction is called, actually the Williamson's synthesis is this one, not the previous one. I'm sorry. The next one is the Williamson synthesis. Okay, so the next reaction is this acetylide. Okay, sodium acetylide. So sodium acetylide, as you know, it is acidic in nature, and its Na combines with Br, and carbon sodium bond breaks up easily, and the sodium will combine with Cr and becomes NaBr, and you will get the ethyl acetylide. This is called ethyl acetylide. IUPAC name is different. It is called as ethyl acetylide. Similarly, you can quote another example of nucleophilic substitution reaction, that is with the silver salt of the carboxylic acid. So silver salt of our carboxylic acids so results in the formation of the ester. So it results in the formation of ester. So you can see RCOO C2H5 ester formation will be there. So if you want to prepare esters from the alkyl halides, so you can use the silver salt of the corresponding acid, and you will get the ester. So if you use the silver acetate, you will get the ethyl acetate as the product. So okay, these are the some of the nucleophilic substitution reactions, so related to the haloalkanes. Remember, in all the cases, in all the reactions, so you can see here, in all the reactions, this bond is going to be cleaved. So in place of Br, in place of halogen atom, Br is more suitable here. So in place of Br, all the nucleophiles will be joined, and this Br will be sent out, and with the other species, it forms the product. So nucleophilic substitution reactions are the common reactions of the haloalkanes. Okay, so next we shall see some of the special features, particularly so this one, why potassium cyanide is going to give ethyl cyanide, whereas the silver cyanide is going to give you ethyl isocyanide. Why potassium nitrate is going to give ethyl nitrite, whereas the silver nitrite is going to give you nitroethane. In the next slide, so that information is given, that is here. So it is given in the as the note. So KCN, that are potassium cyanide, as I told you earlier, KCN is predominantly ionic, and it provides cyanide ions in solution, which is ambidentate nucleophile. Okay, so ambidentate nucleophile it becomes, therefore, so only cyanides will be formed and bind with the carbon side to form a major product. While AgCN is a covalent and form isocyanide as the major product. So it is the major product is the isocyanide, because since it is its covalent nature doesn't break this Ag and Cn. Okay, whereas KCN breaks up easily. becomes K plus and Cn minus. Predominantly it becomes an ambidentate, and whereas this one, since it is covalent in nature, it doesn't bind properly, so it doesn't break properly, and therefore the ethyl group attaches to the nitrogen atom. It becomes isocyanate. Similarly, so like KCN and KNO2, KNO2 form RONO, while AgNO2 produces RNO2 as the product. So here you can see, similar to the KCN and AgCN, so KNO2 and AgNO2 forms the same product. So KNO2 is more ionic, whereas AgNO2 is more covalent, and it becomes ambidentate, whereas this one is going to provide you the unshared pair of electrons of the nitrogen to form the bond. So RNO2 nitroethane alkanes will be formed. So another point regarding this one, vinyl chloride is less reactive towards the nucleophilic substitution reactions due to resonance. In one of the halo compounds, vinyl chloride, in the previous examples you can see. So vinyl chloride possesses the CH2 double bond CHCl. That vinyl chloride is a typical example for the resonance. That resonance increases the stability of the vinyl chloride. Therefore, the nucleophilic substitutions reaction is less reactive. Okay, so these are some of the things you have to remember regarding the physical and chemical properties of the haloalkanes. Thank you very much, and thank you for patient hearing, and I am going to continue the special reactions of the substitution reactions, SN1 and SN2 reactions, in the next part, that is part 3. Thank you.